Hello everyone, I'm Yuanyuan Yao from Zhejiang University. It is my honor to introduce our work, Simple TS, an efficient and universal model selection framework for time series forecasting. The outline of my presentation is listed here. First, I would like to introduce the motivation of our work. The time series prediction task in the database autonomous service DaaS of Alibaba Cloud plays a very important role. The ability to make accurate predictions is crucial for identifying and addressing issues in a timely manner. Motivated by this, we aim to develop effective time series prediction models that can provide accurate forecasting for diverse types of time series data. In addition, Alibaba Cloud's DaaS run more than 2 million prediction tasks every 2 hours from 4 a.m. to 2 p.m. every day. We also aim to improve the efficiency of model training. Another motivation is that time series exhibit different trends over time, including linear, stationary, seasonal, step, irregular, and multimode. None of the models can perform well in all of the time series data. Second, I would like to introduce the technical challenges of our work. Our aim is to achieve optimal results for various types of time series data by selecting the optimal models, facilitated by a figurable interface for model selection tasks. To achieve this goal, we have 3 challenges: how to achieve higher accuracy with less training time, how to improve the accuracy of the classifier, and how to select the selection features of the source data. Third, I will introduce the preliminaries. Given the current time t and last year observations of a time series data, time series forecasting aims to predict the future edge observations. Our problem is given a series dataset that consists of n time series types. The model selection task is to select n models from a set of m forecasting models perform optimally on n time series types. AutoML is a general term that refers to the process of finding the optimal model among the possible choices of models and their parameters. Earlier proposed AutoML is mainly composed of 3 parts: feature engineering, model selection, and algorithm selection. We will introduce TS2-VEC, which proposes a contrast loss that forces the encoder to learn representations at different scales. It uses instance-wise loss and temporal contrastive loss to encode the distribution of time series. An instance represents an object that generates a sequence of time series data. It uses representations of other time series at timestamp t in the same batch as negative numbers. The losses is as shown in this picture. Next, I will present our framework. As shown in the picture, our framework contains offline training and online forecasting. The offline training includes 4 main components: data preprocessing and model training, AutoML label tagging, soft labeling and clustering, and pipeline method classifier. We will further introduce the details of each component. We have developed an offline training system for the DaaS, which enables users to adjust various parameters for training. First, users can input the name of the database metric they want to analyze, such as MySQL CPU usage, MySQL disk usage, MySQL IOPS usage. Additionally, as there are tens of millions of time series data in the Ali Cloud database, users can choose a certain scale of data for training, such as 10%. Based on the input of the metric name and data size, the system will retrieve the data observed in the past 10 days for the specified metric from the Ali Cloud database. Then the system offers 2 types of models for training configuration: deep learning models, machine learning models. The deep learning models include LSTM, Transformer, Deep AI, Deep Factor, Deep State, GB Forecaster, and BEAS, while the machine learning models include ETS, Prophet, MPTS, ARIMA, Hot Winters, and 2 self-developed models, Period and Linear. For deep learning models, the system provides automatic parameter tuning services, which can enhance model training accuracy to some extent. Finally, in the model selection task, the user can select the specified classifier, such as SVM. In addition, the system provides configuration options for the model selection strategy, including efficiency priority and accuracy priority. The corresponding ranked top K models based on the selected strategy can be written into the configuration file. While we proceed to provide the details of the data pre-processing steps and model training. To prepare the source data for training, we split the long time series data into shorter segments. In addition, before executing self-developed linear and period algorithms, we use Kalman filtering to smooth the source data in order to prevent outliers from affecting the shape of the source data. After data pre-processing, we prepare a TS2-VEC model for the following data classification. We propose the weighted representation only. The overall loss is redefined as follows. The weight is manually set. The larger association between instances, the larger value will be set. Next, we pre-train deep learning models based on user-selected parameters. We proceed to present a comprehensive overall of the AutoML label tagging. SimpleTS utilizes the selected models for label tagging. When a piece of data has performed the prediction task on all the models, the name, accuracy, precision, and SMAP of the best model, prediction results, and execution time of each model are recorded and stored in the database. After that, we propose a new weighted soft labeling as an enhanced component of the class file and redesign the loss function, which takes the relevance of labels into account. The loss function is defined as follows, where K is the number of labels, target denotes and encoding of the target classification type. Additionally, clustering is an effective solution to further improve the accuracy of classification. For example, when dealing with the periodic time series data, transformer and deep AI models tend to yield poor results, while Prophet and Hot Winters models demonstrate superior performance. In this way, we can group models that have similar performance into clusters where the number of clusters can be configured, M clusters. Finally, we continue to train a classifier. We replace the source label that represents the best performance model with the clustered labels and then use the pre-trained weighted representation learning model to encode the original data and feed the encoded data into the classifier. This classifier will be further used for online forecasting. For the online prediction task, first, we load the pre-trained weighted representation learning model and encode the source data. Second, we classify this encoded data into the certain type by loading the offline trained classifier model. After that, we can choose the method with the best accuracy or the least execution time from the configuration file according the user's choice. And then we invoke the corresponding time series forecasting model to perform the prediction task. Then I would like to show the experimental evaluation of our work. We utilize 3 private Alibaba database and 52 public datasets. In the experience, we compare simple with 14 time series forecasting model and 3 model selection frameworks, including AISTM Transformer, Deep AI, ETS, Prophet, MPTS, ARIMA, Hot Winters, Deep State Defector, GP Forecaster, Embeds, Private, and Linear, and global based auto forecast and auto AITS. And The performance metrics is train time, predict time, accuracy, precision, and SMAP. Comparing performance results of SimpleTS and the competitors, SimpleTS has the least training time compared with global best AutoForecast and AutoAITS. Although the training time for SimpleTS is the least, its performance in terms of accuracy, precision, and SMAP is the best in most cases. Forecasting accuracy-based ranking of SimpleTS and SOTA toolkits for 15 UCR datasets show that SimpleTS ranks 1 in most cases. We also do comparative experience on MySQL CPU usage, Roseman, Walmart dataset, which have different relations between instances. The result deficits the corresponding results on MySQL CPU dataset. The accuracy and precision reach the peak when the weight of instance loss is set to 0.5. However, on Roseman and Walmart datasets, the accuracy and precision reach the peak when the weight is set to 0.7, as shown in the shape figures. The shape of different instances on MySQL CPU usage differ a lot, but are similar on Roseman and Walmart datasets. That also explains the necessary of combining the time stamp loss and instances loss. We evaluate each technique of the SimpleTS, including representation learning, self-delivering, and clustering. As results show, representation learning outperforms artificial feature engineering in all 3 classification problems. Besides, the results on the comparison of with cluster and without cluster show our optimization technique. Self-delivering works for different classifiers and different datasets to evaluate the effect of clustering. We set the number of clustering into 3, 7, and 14, and we classify the encoded data based on the clustering labels. The result shows classifier performs better in terms of most of the performance metrics after using clustering. In conclusion, in this work, we propose the first framework that incorporates a classifier to distinguish types of time series for prediction. SimpleTS employs clustering and self-developed self-delivering. This way, the prediction accuracy is almost independent of the number of candidate prediction models. Moreover, we propose a weighted representation, a learning strategy for further improving the accuracy of the classifier. Extensive experience on 55 datasets show that SimpleTS outperforms 17 baselines in terms of training time, accuracy, precision, and SMAP in most cases. Thank you. That's all.